These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Let's try this problem.
So, well, huh, well,
Let's check our factoring there. I think we talked about this in a previous session. How do you check whether you've factored correctly?
we distribute the x
And see if you can get back to where you started.
yeah,
So check that and see if that, how can you tell that was incorrect?
because 72 is in a sign, and based on this line, it would be 72x, and that's not the case.
That's right. Okay, well, let me give you a little help with this.
Okay.
So let's erase the last line that you have there on the screen. You're right that we need to factor. Before we factor, factoring will be difficult here as long as we have that coefficient in front of the x squared. So the first thing you should do is divide both sides of the equation by, well, what's the coefficient for the x squared?
3.
So let's divide both sides of the equation by 3. Is that legal? Well, yes, we can do anything to the left side of the equation as long as we also do it to the right.
This is 1, 2, 23, 24. Yeah, 24. Oh, sorry.
Good. And you can see how much easier this will be to work with. So that's an important technique. Now, the next thing is, you're right that it would be nice to factor here, but we need a special... Can we factor an x out of all 3 terms?
We cannot.
So what we need is...
Like this?
That's right. That's what's called in high school reverse FOIL. So we need to use the reverse FOIL technique. Let's see if we can apply that here. Okay, good. How can you check whether you've done reverse FOIL correctly?
We can FOIL this expression.
Yeah, you can do forward FOIL and make sure you get back to where you started. So would that give you the right expression?
Yep.
Good, but that's always something that's important to check. Anytime you factor, you have to use the distributive rule to make sure that you factored correctly. And anytime you use reverse FOIL, you have to use forward FOIL to make sure that you've reverse FOILed correctly. So really, this is a type of factoring, but it's a special type. Okay, now you got the right answer. What is your justification for saying x has to be 6 or 4?
Because we're saying that this expression equals 0.
Yes.
So since this expression times this expression equals 0, so as long as one of them is 0, then it's true. So if we set x equals to 6, then that's 0, which makes the whole thing 0. Or if x equals 4, then it's also 0, which makes this...
Good. Okay, so I wanted to make sure that that was clear. So notice that the first thing you did here was crucial, which is that you got 0 on one side. A lot of students would miss that. Notice that it would have been futile to factor while there was still a 72 on one side. So that's an important step. Sometimes people make that mistake. Sometimes they start factoring before they've gotten a 0 on one side, but that would be futile because then we couldn't use the technique you were just using. Because if you think about the reasoning you just gave, it was crucially dependent on there being a 0 on one side. So your first step was a good step where you moved the 72 with everything else so there would be a 0 on one side. So what's the technique we just went over? This is what's called a quadratic equation. So we're reviewing the high school algebra technique here of how to solve a quadratic equation. So you remember the first step correctly. The first step is get a 0 on one side. Then the next step was where we got stuck. Remember, you always have to check your factoring to make sure it's correct. Notice that one technique that was very helpful here was it's difficult to do reverse FOIL unless the coefficient on the x squared is 1. It's possible, but difficult. So if the coefficient on the squared term is not a 1, you want to divide by that so it will be a 1. Otherwise, it would be possible but difficult to do reverse FOIL. The new equation was much easier to reverse FOIL. Then we do reverse FOIL, and we set each factor equal to 0. So we needed to review that technique. I'll go back to my screen.
Okay.
So I think this was the equation you ended up with at one point. So let me just say, I think it would be a little bit better then to do the next step as this.
Okay.
This is technically your justification for what you're doing. You're saying that if this times this equals 0, then either the left-hand side has to be 0 or the right, and then you can say x equals 4. Now, this is basically what you were doing in your head, but it's a little bit clearer to us if we actually write down that these are the two equations. So the point is that a quadratic equation can actually be split into two separate equations, and then we can solve those if we use that approach. Okay, so this is an algebra technique that we'll need for the next portion of the calculus course. All right, so we reviewed that technique. Let me write this down. Let's try this problem.
Okay. So 4x cubed squared minus 32x plus 60. Okay. So now we can divide both sides by 4. And we get x squared minus 3x plus 20. And now we can reverse FOIL this. Trying to get negative 8x and plus 20. How did I do this wrong? Plus 4x squared minus 32x plus 60 equals 0. Divided by 4, x squared minus 8x plus 20. Oh, yeah. 15. Okay. Okay.
Okay, good. Excellent. All right, so that's a good review of that technique. So again, this was the problem of how to solve a quadratic equation, and we did that correctly. You did make an arithmetic mistake, but the important thing is that you realized that and you went back and caught it. So that's good. It's always important to catch those mistakes. Yeah, since most people are not so good at arithmetic, it's perfectly okay to do the arithmetic in your head, but then you should check it on your calculator anyway. Since people really, especially on the exam, since people tend to make a lot of careless mistakes on that. Okay, but you found what was going wrong there and then you fixed it. Okay, good. Okay, so that's the algebra that we'll need for this section. We got that down, so let's move on. All right, so what we're going to start working on now is applying calculus to word problems. So in a way, that's good because now we're going to finally start to see how calculus can be helpful and apply to the real world. But in a way, it's bad because word problems are tough. And they can be quite time-consuming to learn how to attack them. But we'll do the best that we can here. So let's see. So one of the concepts we'll be working with is the concept of position. Well, let's actually say we're going to be focusing here on linear motion. That is when something moves in a straight line. And actually, you're probably going to be focusing, the problems are most likely to be probably vertical motion. It's possible you might see a horizontal motion problem, but all the problems that you've sent me could be interpreted as vertical motion. So let's focus on that. So let me give you an example of vertical motion. Would you agree that the movement of my pencil now, this is vertical motion?
Yep.
Okay. It's complicated. Sometimes it's moving up, sometimes it's moving down. So we're going to be solving problems like this, where objects are moving sometimes up, sometimes down, sometimes changing direction. So what are the concepts that are required to analyze motion, or vertical motion? First concept is position. Do you remember from class what the symbol is that your course is using for position? No, I'm sorry, excuse me. I changed my mind. The first concept we're going to do, is time.
Okay.
That's even more important. So let's start with the concept of time. Okay. Do you remember what's the symbol that we're using for time?
T?
Good. Uppercase or lowercase?
Lowercase?
That's right. Okay, so that's a logical symbol. We'll be using T for time. What are the units that your course is using for time?
Seconds?
That's right. What's another unit that could conceivably be used for time?
We could use minutes or hours.
Absolutely, yeah. So you could see a problem about minutes or hours, but I think all the problems that I've seen from your course were based on seconds. So that's what we'll focus on. Okay. Okay. So it's pretty apparent how that could be applied here. So for example, you might talk about where is my pencil 1 second after it starts moving, or where's the pencil 10 seconds after it starts moving, or where's the pencil 30 seconds after it starts moving. So that's what the time variable is going to be telling us. It tells us how much time has elapsed since the beginning. So what time do we assign to the very start?
0.
Yeah, so the very beginning will be called time equals 0. And all the other times will be after that. So on these problems, I don't think we're ever going to see a negative time, because t equals 0 will be the beginning. Okay, I think that completes our discussion of time. So now we can move on to position. Now, do you remember what symbol your course is using for position?
I can't recall.
So this one is not nearly as obvious. Here we're using S.
Oh, okay. That's right.
S for position, even though that doesn't quite seem like a logical symbol. Do you know what units your course is using for position?
I'm not sure.
Here we would use feet.
Okay.
So what are other units we could use for position besides feet?
We could use meters.
Or inches, yeah. But
Inches.
I think in your class you're generally using feet. Okay, so since we're focusing on vertical motion, we don't need an x, we're going to be focusing on movement on a y-axis. So, for example, right now the position is 1. Now the position is 3. Now the position is 0. Now the position is 5. So what would the position be now?
3.
How about now?
1.
Okay, so that's just to illustrate what we mean by this concept of position. Actually, your course might not even have used this term, position, but it's using the concept and we need to give it a name. So the name here, they might have just called it S. And that, in your class, it might be thought of as distance, because this is how far you are from the bottom. But I think position would be a better term for this. Now, would you agree that position actually is a function of time?
Yep.
Because if the object is moving, it'll be at different positions at different times. So position could be written as S of t.
Okay, that makes sense. I was wondering what S of t really meant, but
yeah, that's important. So we can't start attacking these word problems unless we know exactly what the symbols are standing for. So what is going to be our independent variable in the problem? Are you familiar with the terms of independent and dependent variables? Yeah, so what's going to be the independent variable?
Time.
Yeah, and what will be the dependent variable?
Our position.
That's right. Good. Now you can see how this will require us to adapt a little bit, because what we've been practicing is functions that look like this. We've been practicing problems where the independent variable was x and the dependent variable was y, so now we're going to have to be flexible and shift to some new symbols. But the method should be the same. We're just going to use t where we used to use x, and we're going to use s where we used to use y. Okay? All right, so that's the concept of position. One of the most common examples we're going to be focusing on now is an object that is thrown upwards from the ground. So if an object is thrown upwards from the ground, what would its path look like? How would it behave?
Well, it would start from 0 and it would move upwards to a point, and then it would eventually come back down.
Good. That's pretty simple, but you have to have that mental picture in your mind before you start doing the math. So what you said is correct. So if the object was being thrown upwards, just like you said, it would start here, and now here it's moving upwards. But your common sense tells you eventually it'll come to a halt, or eventually it'll change direction and then come back down and then hit the ground again. Good. So that's how position would behave if an object is thrown upwards and then comes back down. Good. By the way, have you taken physics?
I haven't. I'm taking it in the fall.
You said you have not?
Nope.
Okay, yeah. So anyway, this is, did you take physics in high school?
I did not.
Okay.
No.
Anyway, this is a sneak peek at some concepts in physics. This is pretty typical physics material. Okay. So in any case, let's see. Okay, I think that's our basic concepts now for position. When I first asked you what the units were for position, you weren't quite sure, but now we can see why feet is a logical unit for position. Okay. Oh, let me ask you actually something else too. Let's say that we start here, and then we move to here, and then we move to here. So the object was thrown upwards, moved up to here, and then moved down. What was the total distance traveled?
8 feet.
Excellent. Because first we moved 4 feet up and then 4 feet down. Anyway, I just wanted to point out that's why in your class they might have called S distance, but that's really not a good habit for a beginner, because S is not distance. Notice that you started and ended at S of 0, but that doesn't mean the distance was 0. So that's why I think it's important to introduce this term position, even if your class doesn't use that. Even though sometimes the class might say S is distance, it really doesn't represent the distance. It represents your position. The distance is something you have to figure out Notice that you had to figure out the distance by breaking the trip up into parts. You figured out the distance for the upward portion and then the distance for the downward portion. That was the only way to solve it. So some of the questions in the homework here ask about the distance traveled. So notice you can't figure that out directly just from the position, but you can figure it out indirectly by thinking about the path that we followed. Okay?
Okay.
All right, so now we need to move on to a more difficult concept. The next concept is velocity. Do you know what the units are for velocity in this section of the course?
Feet per second?
Yeah, do you see how those would... So velocity is something you might already have some intuition for, because it's a term that's used in ordinary life. So what is the velocity? So in ordinary life, we don't usually use feet per second for velocity. Can you think of any other units that we very commonly use for our velocity in ordinary life? Let me just say that as far as we're concerned, we're going to use velocity to basically mean speed.
Okay. So in everyday life, we use miles per hour.
Okay, good. That's all I wanted to get to here. There's actually a technical difference in physics between speed and velocity, but I don't think we need to worry about that in your calculus course. So we're going to say speed is about the same thing as velocity. Okay, yeah, so we're used to measuring our speed when we're driving. So we're used to measuring speed in miles per hour. But here we're going to be focusing on feet per second. Now, what are seconds the units for?
Seconds are the units for an hour.
For time.
For time. Oh, okay. Sorry.
And
yeah,
what
for
are
time.
feet the units for?
For position.
That's right. So notice that velocity is based on comparing position over time. So let's say that you're driving at 60 miles per hour. What does that mean? How would you interpret that in words?
You're traveling 60 miles over the course of, over the course of an hour, you're traveling 60 miles.
Yeah, that means that if you travel for one more hour, you'll travel 60 miles. But now, if you think about it, that's not quite right. If I tell you that I'm driving 60 miles per hour right now, what that really means is that over the next hour, I will travel approximately 60 miles. Unless we assume that the speed never changes, right? Mm-hmm. If you're driving 60 miles per hour now, that doesn't mean you're going to be driving 60 miles per hour for the entire hour. So the 60 miles per hour is only telling you the approximate distance you're going to travel, as long as the speed doesn't change very much. If the speed is constant, then you'll travel exactly 60 miles in an hour. But if the speed is gradually changing, you're only going to travel approximately 60 miles in an hour. Anyway, the reason I wanted to phrase it that way is that should remind you of something. That should remind you of, remember in the past I've oftentimes asked you to interpret derivatives. Well, what I just said should remind you of the way we've been interpreting derivatives in the past. And that's a clue that the velocity actually is a derivative. What's it the derivative of? It's the derivative of the position. So what would be a good symbol then for velocity? If position is s of t and the velocity is the derivative, what would be a good symbol for velocity?
We could use s prime of t.
That's right. Derivatives tell you the rate that something is changing. The derivative of s with respect to t tells you the rate at which s is changing. Well, the rate at which the position is changing is your speed, or your velocity. Okay, so I just tried to give you a couple arguments or explanations for why the velocity is the derivative, but we don't have the time to go into that in too much detail, so we'll also just kind of have to memorize that. The velocity is the derivative of the position. But the basic reason is that the derivative of the position is the rate of change of the position. Well, the rate of change of your position is your speed, if you just think about it. So that's kind of a little proof that the derivative of s with respect to time really is the velocity or the speed. Okay, so that'll be important. Remember we said earlier that our independent variable is going to be t, and our dependent variable would be s. But actually we have now two dependent variables. We have s and we have s prime, because we have now two separate functions, s and s prime. Okay. All right, now the next concept is acceleration. Acceleration is a very difficult and subtle concept. It takes a long time for people to learn what this means in their physics course. In fact, most people who take physics, I don't think, ever really do learn what acceleration means, even though that's one of the main points of the course. So we're not going to have time to go into all, to really get a very clear understanding of this. We'll just try to approach this a little bit mechanically so we can get the word problems correct. So the units for acceleration are feet per second per second. So you can already see how this is a subtle concept because the units are so complicated. So for example, your acceleration might be 32 feet per second per second. So we'll just try to briefly understand what this means. Well, notice that the units on the bottom here are seconds. What concept do we measure in seconds?
We measure time in seconds.
That's right. Now the units on the top are feet per second. What concept do we measure in feet per second?
We measure velocity in feet per second. Or
yes, velocity.
Whatever.
So basically then the acceleration is going to tell us the rate at which the velocity is changing. Remember that the velocity was the rate at which the position was changing. Well, the acceleration is the rate at which the velocity is changing. For example, on Earth, this is the acceleration due to gravity, 32 feet per second per second. So, for example, if you drop something, well, immediately after you drop it, it'll have no speed because it just got dropped. But then 1 second later, after 1 second, it'll be moving at 32 feet per second. Then after 2 seconds, well, notice that every second, the velocity is changing by 32 feet per second. That's what the acceleration tells us. So after 2 seconds, it would be moving at 64 feet per second. You know this. You know from common sense that if you drop something, it'll start moving very slowly, and then it'll move faster and faster and faster, right? If you drop something, it'll just keep speeding up faster and faster until it hits the ground. So after 3 seconds, how fast will it be moving? Well, another second will have passed, so the velocity will have changed by 32 feet per second again. So it would be 64 plus 32, which is 96 feet per second. So let's see if we're getting the hang of this. How would you calculate how fast the object would be moving after 4 seconds?
We would add another 32, so it would be 128 feet per second.
Pretty darn fast, huh?
Mm-hmm.
Right, in just 1 second, it's moving 128 feet. You know that 6 foot tall is like a pretty tall person. So that's the force of gravity. Even after only a few seconds, the object would be moving quite quickly. Okay, so anyway, hopefully we're getting a little bit of a feel here for what the acceleration is. Just like the velocity tells you the rate at which the position is changing, the acceleration tells you the rate at which the velocity is changing. So I'll say that again. The acceleration tells you the rate at which the velocity is changing. And hopefully now we understand what these complicated units mean a little bit more. Okay. So anyway, what do you think would be a good symbol for acceleration then? If the acceleration is the rate at which the velocity is changing, can you think of any symbol we could use for that?
We could, well, the rate of change is the derivative, so derivative of velocity. So velocity is already s prime of t, so the second derivative of s of t.
Excellent. Very good. That's exactly the right logic. What's the symbol for that?
S prime prime of t.
Okay, very good. Excellent. That's right. The acceleration is the second derivative of s. Remember that derivatives are rates of change. The velocity is the rate that your position is changing, so it's the derivative of position. And then the acceleration is the rate that the velocity is changing. So the acceleration is the derivative of the velocity. Well, the derivative of a derivative is a second derivative. Okay, so good. I hope that makes sense to you. Your logic was correct. But we can also just memorize that for doing the word problems. We can just memorize that position is s, velocity is s prime, and acceleration is s double prime. But hopefully we have a feel now for why that makes a little sense. The key here is, we haven't talked about this much in the past, but derivatives are rates of change. Derivatives are rates of change. And the velocity is the rate that the position is changing, and the acceleration is the rate that the velocity is changing. Okay, good. So let's see. Okay. All right, so this is the equation that describes the motion of the object. I've said this is an alien planet because this is not the equation you would use on Earth, but some alien planet with it. So this has a different gravity than the Earth, so it would give us a different equation. Okay, so now let's see how we could solve these types of problems. So let's say, let's try this. One sec.
Okay.
Okay, let's try this.
Where's the ball after 0.5 seconds? Okay. So I'm just going to write A. Where velocity equals 18 feet per second, and S of t position function. Okay, so we're trying to find the ball after 0.5 seconds. And S of t is a position function. So .25, 1/4 of 3. Okay. Where's the ball? Well, the ball's thrown on a certain 18 feet from original position, 8.25 feet from original position.
Good. That's good that you really answered the question. The most important thing there is that you put in the units. Your instructor definitely wants you to put units on these problems. That's one reason why we were reviewing the units earlier. So it's good that you did that. 8.25 feet above or below the original position?
Well, I guess it depends, but I'm going to assume above.
Did our answer come out positive or negative?
Oh, okay, you're right. Positive.
So we're generally going to assume that the positive direction is up in this case, like a normal axis. But also, you could tell that from your common sense, right? Well, not necessarily, but I guess on these problems, we're generally going to assume that something is being thrown basically from ground level. So you could just say 8.25 feet above the ground, probably. Although above the original position is actually a little more accurate. Good. All right. So the important thing here is to make sure you've identified the question. I'm going to go back to my screen then for a second. I would encourage you on these problems to always start by writing down a question mark for what the question is asking us. What would be a good symbol for what this question is asking us?
Okay, well, it's asking us where is the ball after 0.5 seconds. So it's asking us the position. So S
Good.
of 0.5.
So that, I think, should be our first step for these word problems. Start by identifying what the question's asking you for by writing down an appropriate symbol when possible. And then you could go ahead and actually figure that out just like you did. And you used a good method. But we won't be able to solve unless we know a good symbol for what the question's asking us for. So that would be a good first step. All right, so anyway, that was good. You did that problem correctly. Let's try this problem.
Okay, where is the ball after 4.5 seconds? Okay, so where is the ball position? Well, this is the same thing. So okay.
Good. All right, that's a good method. The only thing I would add is let's get into the habit of starting by writing a question mark with a symbol for what the question's asking. This was a pretty easy question to get started with, but let's start building that habit. Excellent. Good. And then you found a good way to solve for that. That's good. Okay, good. So I'll go back. So notice questions A and B did not use the word position, but you could tell that that's what they were asking you for. So, good. Let's try this problem.
Okay. Okay, so we're trying to find velocity. Velocity is the derivative of the position function. So s prime of t, well, so first we need to find this. It's the function. I got it down here. Okay, so (18 minus 6t), and then three velocity is feet per second, so 3 feet per second. It says after 2.5 seconds. Okay.
That was a good method. So it's good that you started with the question mark with the symbol. So it's good that you saw it. Now they were asking us for the derivative of s using the work we talked about earlier. And so now you had to use your derivative approach. Let's see. So let's see. Your first line was s prime 2.5 equals question mark. And then can you just read aloud what did you write in the next line? I can't read your handwriting.
Sorry, I wrote s prime of x equals 18 minus 6t. So I took the
now,
derivative.
what is the independent variable in this problem?
The independent variable is time. Okay, is time.
Right. Okay, so I think you see what I'm getting at there. Okay, yes. This is what I talked about earlier when I said we have to adapt a little bit. In our earlier problems, we were always doing y of x. But now we need to change and realize we're not dealing with x anymore. We're dealing with t. So it's better to use that notation. All right, because you didn't actually plug in a value for x, you plugged in a value for t, and you did that correctly. So after 2.5 seconds, will the object be moving up or down?
Up.
How does your answer tell you that?
Because it's positive.
That's right. That's probably something you should have mentioned in the answer then. So the final velocity will be 3 feet per second, which means we're moving upwards. Good. Good. Let's draw a graph of this function.
Okay. The function. The derivative of the function is the velocity, so the slope is 3.
So what I was going for is, so we're not going to do specifically part C here. Let's draw the graph of the original position function.
Okay. So I need to plug in the original function into the calculator so I can see it.
Right.
So 18x minus 3x squared graph. Whoa. Zoom in. Enter. Zoom in. Okay, well, I get something like this. Like that. And this is s of t equals 18t minus 3t squared. And then so this is a okay. So this is the function.
Good.
Graph.
So let's label the axes.
But this is time. Time. Yep, okay.
So what's our independent variable?
Our independent variable is time.
So you labeled that on the horizontal axis. And what's our dependent variable?
The position.
Not y.
Right.
We're just not using x and y here. You might just be in the habit of just thinking that y means vertical axis, but it doesn't. That's just the most common label. So here our vertical axis is s. Okay, I'm going to go back to my screen to show you how to do this on your calculator a little bit more. All right, so we go to y equals, and then the function here was 18x minus 3x squared. Now notice one thing that's confusing is your calculator is not flexible when it comes to graphs. Even though the independent variable is really t, it can only graph it if we tell it that it's x. And even though the dependent variable is really s, the calculator forces it to be y. So we have to adapt to the calculator here, but we need to know that's just for the calculator. Really, the independent variable is t and the dependent is s. Now we'll draw the graph. This is what you got?
Yep, I guess I didn't see the right-hand side, huh?
So
okay,
probably you were starting with it, you were already zoomed in.
Zoom standard.
Do you remember? Yeah, so remember that it's good for a new problem always to go to zoom standard, and that'll take you back to your default zoom.
There we go, I see that now.
And you can see now the problem here is we're not, I think you were misdiagnosing what was our problem here. We don't need to zoom in more, we need to actually zoom out.
Yep.
We actually need to zoom out. So let me show you how to do that. We'll go to zoom, then out. Now I'm going to move my cursor here to tell the calculator where I want to zoom around. So I want this to be the center of my new graph. We'll see how that works. Now I hit enter. It knows I'm zooming because I came from the zoom menu. Okay, there we go. Maybe now we zoomed in a little, now I zoomed out a little bit too much, but at least now I can see the whole graph, basically. Okay. Okay, so now we zoomed out a little bit too much, but anyway, now we're seeing the graph a little bit more clearly at this point, and we can go to trace and then move along the graph. By the way, oh, maybe I'll do this. I'll go to zoom. I only care about the first quadrant because we don't care about negative time here. Do you have a first quadrant option?
I do not. My last prompt is zoom fit, unfortunately.
Okay, too bad. All right. So, all right, we'll just stick with this, what we have here. Okay, but notice we don't care about the negative parts here.
Right.
We only care about this part. So notice if we could, this is a parabola. It might not be totally clear from this level of zoom, but this is a parabola at this point. Okay, so now if we're going to draw the graph, we only care about this quadrant. So the graph would look like this if we weren't zoomed in so much. Now, do you agree that this graph is logical? This is what it should look like if an object is first moving up and then falling back down.
Yep.
All right, so now, of course, this is not the actual path of the object. The object is really moving like this, up, then down, along a single line, but the graph looks like this. Okay,
right.
Good. So let's go back to some of the parts we've done here. Where is the ball after 0.5 seconds? So we would go trace, 0.5, and we can get that's 8.25 at this point, basically, which I think is the answer you got before.
Yep.
Okay.
Cool.
And then we said, where's the ball after 4.5 seconds? Trace x equals 4.5. Now notice that tells us something interesting. At this point, is the ball moving up or down?
It is moving. Well, it's moving down.
You can see because you can see we're on the downward portion, right?
Right.
That's something that wasn't obvious from our earlier work, but we can see that from the graph. Okay, so and maybe going back to 0.5 seconds. At 0.5 seconds, were we moving up or down?
We were moving up.
Because you can see you're on the upward portion. So that's something that the graph can help us to see here. Okay, so now notice this graph will not tell you velocity directly. It's the position graph, not the velocity. Your calculator doesn't do the derivative automatically. Let's try this problem.
Okay. acceleration of the ball. Okay, so acceleration is second derivative over. So just going to rewrite s prime of t equals 18 minus 6t. And the second derivative is negative 6. Okay, so after 1.5 seconds, the acceleration is still negative 6 feet per feet per second Second derivative 0, 6, negative 6. Okay?
Okay, excellent. That's a good method. Remember, let's start by writing down a question mark with what the question's asking us for.
So the second derivative for 1.5 seconds.
Good. Okay, excellent. That was a very good method. It's good that you put in the units there at the end. We memorized that those are the correct units for acceleration. Excellent. So what would be the acceleration of the ball after 2 seconds?
After 2 seconds, it would still be negative 6 feet per second.
That's right. Excellent. What would be the acceleration of the ball after 3 seconds?
After 3 seconds, it would be the same, still negative 6 feet per second.
Because in this case, we've discovered that the second derivative is a constant.
Mm-hmm.
It doesn't depend on the input. Now, you might see other problems on the exam where the acceleration is not a constant. But in this case, it happens to be a constant. By the way, this is something you'll study in physics. This acceleration is coming from gravity, right? It's the gravity that's making the ball accelerate. Does gravity pull things up or down?
Down.
That's why the acceleration is negative.
Okay.
Acceleration is negative because the gravity is always pulling down on the object. And it turns out that one of the discoveries of physics is that the acceleration due to gravity is constant. So in physics class, you'll see why that came out to be a constant. On the other hand, though, you might see other position problems that don't involve moving in position of gravity. You might be moving on a spring or something, so then the acceleration might not be constant. So you can't just always assume that. By the way, remember I told you earlier that on Earth, gravity's acceleration is 32 feet per second per second. I guess I should have said negative 32 feet per second per second. Earth's gravity's acceleration is 32 feet per second per second. So this alien planet, is their gravity stronger or weaker than Earth?
It is weaker.
Because you can see it's accelerating the object less.
Mm-hmm.
So it's probably a smaller planet than the Earth. There's no point looking at the calculator for 1.5 seconds here because it wouldn't give us the acceleration anyway. It only gives us the position. Let's see. Now, remember that the movement of the object is going to look like this. So remember the graph looks like this, but that's not what the object's path looks like. If you drew the object's path, it would just be straight up and then straight down. And in fact, even this is not what it looks like because this should really be right on top of this line. First it goes up and then it goes down. I'm just putting them side by side so you can see the two of them. Okay, so what does it mean when the velocity is positive?
When the velocity is positive,
or when the velocity is negative?
When it's positive, you're moving upwards, and then when it's negative, you're going downwards.
Excellent. So what does it mean when the velocity is 0?
The velocity is 0.
That's a little tricky, so I'll just tell you. Well, obviously, what do you think?
It's the point where the ball's not going up or going down. It's when it's like in a transition state type thing.
Transition state. Which point will that be on the path?
The very, very top.
That's right. So that's a very good answer. Let's phrase that a little bit more clearly. Your velocity is 0. You said it's the transition state. Let's just phrase that a little bit more clearly. Your velocity is 0 at the moment that you're changing direction.
Okay.
While you're moving up, the velocity is positive. While you're moving down, the velocity is negative. The instant that you're changing direction, Your velocity is 0. Now, your instructor says also that this means that the object is at rest.
Oh, that's right.
Although I would prefer to say it's changing direction, but your instructor uses this term, at rest. Okay, so at what point on this path will the velocity be 0?
At the top of the first line?
Yeah, we can call this the peak, which is also the top of this line.
Right.
Because these 2 points are the same instant in time. So the velocity is 0 at your peak. The velocity is 0 at the peak. I don't really like saying that you're at rest because you really are moving. You can say that the idea is that you're at rest for an instant, whatever that means. All right, so your instructor would say that you're at rest at that point as well. But maybe it's clearer to say that that's the point when you're changing direction. Okay. So now I'm going to give you a harder problem.
Okay.
Okay, this problem is a lot harder than the previous ones, but give it a shot, and if you get stuck, I'll give you some help.
Okay. Maximum height reached by the ball. So the maximum height is the peak when it's thrown, and the peak is when velocity is 0 and velocity is the first derivative or derivative of the function. So we're trying to solve this. Equals 18 minus 6, 0. The maximum height is 18 feet. Okay. What do you think? Yep.
Okay, I'm going to go back. Let's see, no, 1 second. 18 minus 6, 0. Okay, I'm going to go back to my screen. I've been telling you to write down a symbol here. That's a little tricky, but what would be a good symbol for what this question is asking us?
We're looking for the maximum height, so that's a position, so S, I believe. Yeah, S.
Now, we don't know what time this will occur. So we can just say S for maximum height. But I don't think that's what you actually solved for in the problem. Did you solve for S prime? So,
right.
Okay, well, let's work on this together a little bit. Now, the key thing here is we're really going to have to do this in 2 steps. Because you can see what the problem is already. You can't figure out S unless you know what to plug in for T. So what's the first thing we need to figure out to solve this problem? Before we can figure out S, what do we need to figure out?
We need to figure out how long it takes to reach maximum height.
Yes, that's right. First, we need to find how long it takes. What would be the symbol for that?
T.
Yes. First, we need T for maximum height. The problem didn't ask us for that, but we really need that. All right. Excuse me. First, we need the T for the maximum height. Now, in order to, so this is a word problem. How do we solve word problems? We solve word problems by writing down equations and then solving the equations. So we need to write down an equation about the maximum height. And you actually did a good job of that because you said that at the maximum height, S prime of T, you were on the right track, but we had a little trouble with that. So we were using S prime of T, and S prime of T on this problem is what?
18 minus 6T,
Good.
I believe. Yeah.
Good. Now, we know you had a good idea there. You were going to use the number 0. What are you plugging in 0 for? What's going to be equal to 0 in this equation? What will be equal to 0 in this equation?
The velocity.
Yeah. Where did the 0 come from? How do you know that we have a 0 in the problem?
Because we're trying to find the maximum height, which is the peak, and at the peak the velocity is 0.
That's right. That's what we were just talking about here. Oops. At the peak, the velocity is 0. And what's the symbol for velocity?
That is S prime.
That's right, not t. So I think you made a mistake in how you were doing this because you were plugging in 0 for t. But we're not plugging in 0 for t. We're plugging in 0 for what?
For velocity.
And what's the symbol for that?
S prime.
So how would you do that? Do you see how to do that? You just do that like this.
Oh, okay. Gotcha.
The left-hand side is S prime. So we're plugging in the 0 for the S prime, not for the t.
Okay, that makes sense.
Now what?
Okay, now we need to, well, first we need to find the time when, how long it takes to reach the max height. So we solve for t.
Good.
And I think 16 was supposed to be 18. So
oh, did we make a mistake here? Let's see.
Just before we move
thanks.
on.
It should be 18 minus 6t. I wrote that down wrong. Okay. Thanks.
So then we solve for t, and t is 3, so it takes 3 seconds to reach the maximum height. So we can go back, and the original question was, what is the maximum height? So we can just use the original function and plug 3 back into the function, and that's our position.
Okay, so let's finish off that problem then.
Okay. So okay, so we're trying to find first how long to reach max height. So S prime t is the velocity is 0. So minus now t equals 3, and now the original function was s of t equals 18. It's t minus 3t squared. So s of 3 equals 36, 46, 54. 18 times 3 is 54. 3 squared is 9 times 3 is 27. So this is just 27. So maximum height reached by the ball is 27 feet.
Okay. All right, so you can see that was trickier, but I'm pretty sure you'll see a question like that on the exam. All right, so this was trickier because we had to actually break it into 2 parts. Before we could find the maximum height, we had to figure out how long it takes to reach the peak. Remember, how do you solve word problems? By writing down an equation. So what was the equation we ended up writing down? The key equation was the 0 equals 18 minus 6t. That was the key to the problem. 0 equals 18 minus 6t. Once we had that equation, we could solve for t. The tricky part was coming up with that equation. So remember, how did we go wrong the first time? You started well. You wrote s prime of t equals 18 minus 6t, but then, and you saw you had a 0, you just plugged the 0 in at the wrong place. You plugged it in for t, whereas t is what we don't know. We're actually plugging the 0 in for the s prime. So that's the tricky part to really highlight there. We're plugging the 0 in for s prime, and then going backwards. I can see why you got confused, because usually we start by plugging in the number for the independent variable, and then we find the dependent. But in this problem, we did the reverse. And then we had to go back and then plug that into our position equation as well. Okay, so that's an example of how to do that. I think I'll go back to my screen. Let's look at this on the calculator. Couldn't we kind of solve this on the calculator? Do you see what I mean? So if I go trace, which point is this problem talking about?
3. Yep, and y is 27.
All right, let's see. Whoops.
Which is the peak.
Yeah, but of course, you already, in order to do that, you had to already know the time. So if you were just tracing, notice that if you trace and you go to the top, on my calculator at least, at the peak, I have x equals 2.7, which is close to 3. Which is close to 3. If I zoomed in, and now I can trace and go even closer to the peak. Now I can see that at the peak, it's saying it's 2.97. And if I zoomed even further, I can see it's even closer to 3. So you can kind of solve this on your calculator a little bit. If you really zoom way in on the peak, remember that what the calculator is calling x is what we're calling t. So if you really zoom way in on the peak, you can see pretty clearly that about 3 seconds have passed to get there. All right, so technically we don't need calculus to solve this. Obviously your instructor won't give you credit unless you use the calculus, but we can kind of also see that we could solve this by looking at the calculator, or at least confirm our answer on the calculator. Okay, good. Let's go ahead and do something else that you'll see on the test here. Okay, let's try this.
8 meters after t seconds is given by h of t equals 9t minus t squared. Okay. What is the max height reached? Well, this is a position function time. So first we need to, how long does it take to reach max height? And also at max height, s prime of t equals 0. Okay, so first we need to find s prime of t, or h prime of t. equals 9 minus 2t. And the velocity is 0, 9 minus 2t. So negative 2t equals negative 9. T equals 9 over 2. Okay, so now we can plug that back into h of 9 over 2 equals 9 plus 9 over 2 minus 2 squared. Well, I think this is 9 again, but 9 times go. Okay. Just double check this. 9 times 9 divided by 2. 40.5. Okay. So max height reached. This is the function. This is the position function. It's asking us the maximum height reach of the ball. Well, to find that, we need to know how long does it take to reach max height because our function is based around time. So we found that define how long it takes. We have to find the derivative of the function and then set the velocity to 0 and solve for t, which shows us how long it takes to reach the peak. And then we take that time value and plug it back into our original function, and that gives us the height at the peak, and we could double check that on the calculator by graphing the function and tracing over to the peak, and the y value should be 20.25. Or, yeah.
That's a good discussion. Did you copy the problem onto a piece of paper?
Nope.
Oh. You didn't copy the original problem?
Sorry, yes I did.
Can you read out what you have written down?
Yep. A ball is thrown vertically upward from the surface of a different planet, and its height in meters after t seconds is given by h of t equals 9t minus t squared. What is the maximum height? Sorry, it should be meters.
Okay, good. There you go. All right. Now, it's good that you remembered to put in the units there, but it would be a shame to do all that good work and lose some points for the units, and that's something your instructor definitely cares about. Your instructor definitely wants us to use the correct units on these types of word problems. So I kind of led you astray here, because when we were doing the introduction, I said that the units for position would be feet. But it looks like your instructor actually likes to mix things up. So you'll have to pay attention to the problem to see what the units are actually going to be. So this is a problem from the sample test that you sent me. So it looks like, except for the units, we would have gotten that right. So that's good. Remember, the big mistake to watch out for is don't plug in 0 for t. Plug in 0 for h prime. And you did do that. Also, I notice here they didn't use s, they used h. So again, they're mixing things up a little bit. Instead of s, they're using h. But you saw that they were using h basically to stand for the same thing that we were using s before. H is actually a more logical variable because the position here is a height. So this is for the same problem we were just working on. Did we call this a rock or a ball? I forget. It's a rock.
Yeah, that's fine.
I'll give this a shot.
Okay, as it was in 18 meters on the way up. Okay. The way up. Okay.
Now take your time and give it some thought.
after okay, so our position function equals 9t minus t squared, and just to have this, our velocity is equal to 9 minus 2t. Okay, so what is the velocity of the ball after it has traveled 18 feet on the way up? Well, how long did it take to get to 18 feet? Well, we can figure that out by setting the original function to 18 equals 9t minus t squared, and then solve for t. So, okay, so t squared minus 9t plus 18 equals 0, and then t okay, so it took, well, I was trying to figure out how long it took to reach 18 feet. So I guess it paused for 3 seconds in the air. I don't know. Okay, I'm going to go with this. But, so that was our time. And then what is the velocity at 6? I'm going to find both of them. Equals 9 minus 12, negative 3 feet per second. And then h prime of 3 equals 9 minus 6, so 3 feet per second. Okay, so, well, yeah, it's kind of strange, I guess, because this would be going downwards and this would be going up. But we just said the maximum height was 20.25. So at 6 seconds, the height would be 36. 54 minus 36.
Why are you plugging in 6?
Yeah.
Oh, okay. Yeah, I see why. Sorry.
Yeah. It'd be 18 feet. Okay. Yeah. This is correct then.
So what's the answer?
What is the velocity of the ball after it has traveled 18 feet on the way up? Well, this is up, so the answer is this. The velocity of the ball after it has traveled 18 feet on the way up is 3 feet per second.
Okay. Yeah, I think we got confused about the units. I think you've miswritten the problem on your screen.
A ball has thrown its... Yeah, I must have traveled 18 meters.
Right.
I don't know. I'm sorry. Okay.
So that's something to watch out for. So your instructor on the test might use meters, feet, inches, miles. They might use anything that might be different from what you practiced. So it's important to pay close attention to that, because that was the only mistake you made. So it would be a shame to lose credit for the unit. So that is something the instructor is going to be grading on there. Okay. Now, do you understand why the algebra gave us 2 different answers? What's the significance of that? Why is there answers both t equals 3 and t equals 6?
Because because this point is our peak and our velocity.
Which point is our peak?
18 meters.
And that's actually a mistake. Why are you saying that that's the peak?
Well, I'm
we
not
actually
sure
figured
how.
out the peak in the previous part, right?
Right. Okay.
What's the actual peak?
20.25.
Yeah. Why don't you draw a graph of the position function here?
I think I have that in here. So
this is a new problem, so you'll have to graph it.
Okay. 9x minus x squared. Let me zoom out. Zoom standard. Okay. Well, I didn't draw that very well. Okay, this is our function.
Good. If you actually wanted to see the whole thing on your calculator, you probably had to zoom out once or twice. Put a dot, well, let's label the axes. Good. Put a dot at the peak. Now label the coordinates of that point.
Okay. 20.25 and 9/2. So
let's put the units on those coordinates so that we can remember what they stand for. And let's write the 9/2 as a decimal. Okay, excellent. You could confirm that on your calculator by tracing, and you'll see that's the peak, but we already know that from the previous part of the problem. Now, label the point that we just figured out on the part of the problem that we just did.
Okay.
What's the point that we were focusing on now?
Somewhere around here.
Excellent. So, let's label its coordinates.
So it was 3 seconds. And 18 feet from the problem. Oh, sorry. Meters.
Yeah, we have to watch out for that on the test. Good. Notice that this problem was in a way a little bit easier than the earlier one, because the earlier problem didn't tell you the first or the second coordinate. We had to figure out both of those, both the 4.5 and the 20.25. This was a little easier because, as I think you were mentioning, this problem gave us the h coordinate. It said 18 meters, and we just had to figure out the t. And then we had to go on a little bit more and do some other stuff. All right. So anyway, remember that when we were solving this problem, we got the algebra gave us 2 t's, 6 and 3. Can you see why it's giving us 2 t's? Label the point that corresponds to the other t.
The other t is.
Remember the other t? What were the 2 t's that we got?
We got okay, at 3 seconds and 6 seconds.
That's right.
So right there. Okay, that makes sense. Yeah. So this was 6 seconds. And it was the same.
Can you see why the math is so? What were you asking your math to do? You were telling the math when are we going to be at a height of 18 meters? right? You were asking, hey math, when are we going to be at a height of 18 meters? And the math said, well, there's 2 times that will happen. Well, that's just common sense, right? You'll be at 18 meters on the way up, and then you'll pass 18 meters again on the way down. And you can see that here from the graph. Notice that 3 seconds is before the peak. So then that's when we were on the way up. And then we hit that same 18 meters again on the way down. There was something that you said here. There was a point here when I think you were confusing the 2 parts of the problem, and I think you were thinking that we were going to be at the peak after 3 seconds. But remember, no, the peak is 4.5 seconds. This is a whole different part of the problem. Also, at one point you said something like, oh, we're going to pause here. But notice there are no pauses. You know, just think about your common sense. When you throw a ball upwards, it never pauses. It moves smoothly upwards, then it changes direction in an instant, and then it moves smoothly downwards. It never pauses for more than an instant. It certainly doesn't pause for a few seconds. You just know that from your common sense of how objects move when you toss them upwards. So the reason that the algebra gave us 2 answers is there's really 2 times when we're going to be at 18 meters. Scroll back up. One other thing here. There was when you were plotting that point, for a second there you were putting it in the wrong quadrant. I think you might have been thinking that you had to plot a negative number. But remember, h is not negative, h prime was negative. Well, notice we're not even bothering graphing h prime. Notice that 3 meters per second and negative 3 feet per second, they don't even go in this graph. Because we're not graphing h prime, we're just graphing h and t. All right, let's scroll up a little bit. So you can see now why the question was written the way it was. They didn't just say, what's the velocity of the ball after it has traveled 18 meters? Instead, they said, after it has traveled 18 meters on the way up. You can see why they had to say that, because it's going to hit 18 meters again on the way down. So they just had to clarify which one they were talking about here. So we can see why we got 2 different answers in this case. Okay, so that was a part of the problem I think you were having a little trouble interpreting. But actually solving the problem, I think you got this right on your own. I don't think I had to give you any hints. I think you worked the whole thing out on your own. So that's good, because this is quite a lot different from the previous problem. By the way, you can see why we went over that algebra earlier. Here, we finally got to use the algebra we used at the beginning of the session. We need it for solving these types of quadratic equations. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.